Welcome everyone to this week's M2D2 talk. This week I'm very happy to have Minsu Kim with us. Minsu is a PhD student at the Korea Advanced Institute of Science and Technology, or KAIST. That's where he did his bachelor's and master's degree. He's currently interning in Yasha Benju's group, and he's focusing on enhancing GFlowNets in various aspects, and also exploring their application in lots of domains, including scientific discovery. And yeah, Minsu Kim has done a lot of great work on GFlowNets. I'm very happy to hear about his work now. Thank you.
Okay. Hello, I'm Minsu Kim, and today I will presenting our recent project, Local Search GFlowNets. And this work is collaborate with many pupils, like shown in below. And yes, first let me introduce what GFlowNet is. GFlowNet aims to produce diverse combinatorial structures such as molecule graph. GFlowNet trains sequential decision-making policy where terminal states has distribution proportional to the reward. So well-trained GFlowNets will sample high reward and also diverse structures, which will be beneficial for real-world drug discovery. Producing diversified high reward sample is crucial because we have to assume that our score function or the reward function has epistemic uncertainty. So diverse candidates will increase chance to be survived after many screening process of drug discovery. Here, I provide a toy illustration for GFlowNets that only has two terminal states. So GFlowNets models of particle flows. So let water be started from the source. We record the total amount of the water as partition function Z. So here Z equals Rx1 plus Rx2. So X1 and X2 is two terminal states, and these X will be our target structures. And water will flow through these trajectories. And the important point is that there exist multiple trajectories that can terminalize to same structures. And the final amount of the water will at the sink will equals to the leeward. So this probability flow will generate this x1 with probability of Rx1 divided by Z. And also we have probability that produce x2 that equals Rx2 divided by Z. So it is really simple that if we can model these particle flows, we can make an exact sampler. However, in real world, we have combinatorially large space of X, right? So we cannot like exactly measure this partition function, which means the sum of every combinatorial structure's leeward is impracticable. So we have to learn these flow models using neural networks and make these neural networks generalization capabilities to like infer how these flow are, even these states or the flow are not visited in the training. We have to generalize them. That is GFlowNets. So let's go detail for what flow is. So first, let's define what trajectory is. The trajectory is simply the sequence of the states from the initial states to terminal states. So recall our target space is in the terminal states. And from the initial states, we sequentially add some action to produce our target structure. For example, if we want to generate some molecule graph, we started from initial states of empty set, and we sequentially add some component of the atom or fragment, so that we build our target structures, which is terminal states. And this target structure will be evaluated by some levered function that can be some like homolumogaph or binding activity with some our target molecule or protein. So it can be anything you want to score. The flow means that the amount of the particles that is through that sequence of states. And there exist multiple trajectories can lead same terminal states, right? And some of these trajectory flow have to be the levered of these terminal states. And these can be extended to every intermediate state that we can define the state flow, that is amount of water in the specific states, that we can define that by some every trajectory flow that goes through that specific states. Similarly, we can define edge flow, that how many water particles are through that specific edge. So if we can measure this kind of flow, right, we can also estimate the probability of these generating this structure. So in practice, we will use a policy, and we will introduce two policies. So first, for forward policy will generate a child states given parent states. That is really similar with forward in reinforcement learning. So yes, and this can be defined by edge flow from the parents' state to the children's states divided by the parents' state flow. And if we make composition policy from initial state to final states, we have to multiply them over the trajectories. That will be the same with the levered divided by partition function. That's our objective, right? And backward policy is can be similarly defined, but these will models from children's states to the parent states. So we have two kind of policy, yes. And so using this, we have several kind of way to learn GFlowNets. So if GFlowNets satisfy one of these balancing equations, we can so GFlowNets will be an exact sampler. The first condition is detailed balance. That is balance equation of the two consecutive states. So we say detailed balance. So this is really similar with the water flow balance of these consecutive states. And this equation can be formalized like this. We can write balance equation with forward policy and backward policy, and parent states flow and children states flow. Yes. And using detailed balance, we can extend this idea by longer trajectory. So detailed balance is just two consecutive states, but maybe we can consider the trajectories that a length of m, right? So we can we can composite this detailed balance with longer trajectories, and even we can extend this for full trajectory from initial state to the final state. Okay, there is question from Jason.
Oh, hi. Could you explain what a straight line is? Like between S and S prime? What does that mean?
S and S prime. That is transition between parent state to the children states.
So is it different from the arrow?
Straight line? Sorry.
So previously you show, for example, flow from S to S prime. There's arrow from
Right.
S to S prime. So is that the same as the vertical line?
Is there any vertical line here? Vertical?
So for example, in detailed balance at the bottom left corner, you wrote PB as vertical line S prime. So I was a bit confused about what that means. Is that like the condition in?
So F S arrow S prime. Do you mean this?
I'm not seeing your cursor, but um, when you write PB S and vertical line S prime, that is like
Yeah, that's
condition in conditional
conditional
probability.
distribution. Yes, yeah,
Oh,
yeah,
okay, okay.
yeah,
Thank you.
yeah. It's just conditional distribution. Okay, good. Okay, and let's move on. So this is three major variance equation. So you just have to consider one of them. Just so if we can satisfy one of these conditions perfectly, we can make exact sampler, and this will be mathematically equivalent when this balance equation is satisfied. But this kind of loss function is all you need. The answer is not. So if loss value is 0 for every support space, yes, we can make GFlowNets. We can achieve exact sampler. However, complexity of the states, the support states is combinatorial large. So we need a behavior policy that provides training data points for GFlowNets. So we can not train, we can minimize our loss function for every possible state space, right? So we have to choose which space we will learn, and we have to generalize into the unvisited states. So we need exploration. We need some behavioral policy to choose subset of full support space. So GPLS researchers usually use the current training GPLS, which can be seen on policy in the reinforcement learning or its variance. So it depends on the ability of the training policy, right? So this is really similar with reinforcement learning. And as you know, in the reinforcement learning, also there is problem with the exploration. So how to make a proper behavioral policy is really important for final performances. So not only for this kind of balance equation and loss function, we have to consider how to efficiently explore over this complex space. So there is limitation of GFlowNet researches in the exploration. So GFlowNet explore diverse candidates, various modes, and this is very good comparing with the leeward maximization method that only seek a single modes. However, they have problem with our exploration that they tend to not revisit the specific modes. So when they visit some specific modes, they will not do revisit frequently on the same modes and taking higher leeward over this specific region because they try to do diverse seeking. So when you see this kind of leeward sheets, this red star will remains yes, the middle level of lever very diversely. So if you see the performance of the GFlowNet in some molecule optimization tasks, so our expectation of the average lever is 100%, but they only makes 808% of expected lever. So which means their exploration is just seeking a low levered region, right? So I see that can be one of the main problem of the GFlowNet exploration. So my idea is here. So we can use hierarchical exploration strategy. So we can use GFlowNet's ability to find a diverse candidates, right? And so GFlowNet will not revisit same mode frequently. So we can make additional local search given the candidates of GFlowNet exploration. So we can do some local search process over these candidates. So there is diverse candidates that has low levered, but so we can if we use local search, we can make diverse candidate and high levered samples, and we can use them to train GFlowNet again. So yes, that is overall idea. And so this is more formal algorithm, so that in step A, there is 3 steps, and this step ABC will iterate over training, right? So in step A, we samples trajectories from GFlowNets. So let's say we will sample some DNA sequence using GFlowNets. So yes, this is the example. And so we will sample M number of samples. And in step B, we iteratively refine the trajectories by locally destroy and reconstruction using backward policy and forward policy. So recall we have 2 policy, and we can use backward policy to partially destroy the trajectory. And we can also use forward policy by reconstruct these destroyed trajectories. This can be a very good transition corner. And we can use maybe MCMC and some many tweaks to make filter this new proposal from the corner. And this will increase the local regions levered. So yes, this is our idea. So this is more detailed illustration of the back-end force. So imagine that our trajectories is very long. Then GFlowNets or in prior studies, they generate trajectories from the scratch. And so when this sequence length is large enough, they will produce a they have to explore large space, right? If they produce a sequence from the scratch. But what if we start from the complete trajectories and just locally backtrack and locally reconstruct? Then we can focus on the specific local region and will capable to search with local and do some filtering. So we can do 2 kind of filtering strategies that we can accept new proposal when the levered value is improved in local region, or we can even use a metropolis hasting that will guarantee the exact samples, right? So how these samples can satisfy our sampling objects, right? So yeah, this is our idea. And there is another perspective of this algorithm. So we can see this algorithm in MCMC perspective. So let's see the original MCMC gives extremely slow mode mixing. Like they have to sequentially like explore by locally deviate with transition kernel, right? Oh, Emmanuel? Yeah.
Yeah, there's a question in the chat, I think about the last slide.
Okay, so
Yeah, wait. Oh, no, sorry. In the 3-step slide, Prudentius asks, step B looks like an autoencoder.
step
Is that
B. Okay, okay, Prudencio said step B looks like autoencoder is that use just better representation purpose. Yeah, it looks like autoencoder, but it's not autoencoder. Just yes, just for good looking. Yes, just backtrack and yeah, reconstruct. Yeah, yeah. Okay. Good. And so in MCMC perspective, so in some of they have a slow mode mixing time, but we can use GFlowNets that firstly propose very good initial states, and we can run multiple chain MCMC in parallel, so that will make fast mode mixing. So this algorithm can be seen MCMC algorithm that supported by GFlowNets. So also can be seen GFlowNet algorithm supported from MCMC. Okay. So let's introduce experiments. So we verified this local search GFlowNets with 4 different tasks that include very small atomic QM9 generation. So we measure homo-LUMO gap as levers. And we have a fragment-based molecule generation. Yeah, that measure binding affinity as the levered function, and DNA sequence problem that also aims to maximize binding activity, and RNA bindings also maximize binding activity. And so, and here's the point. So when we generate the sequence, let's say DNA sequence, as seen in this illustration, so maybe many people just generate this sequence from left to the right. So there's only one path, right? And one sequence has only one trajectory. This equals the backward trajectory should be 1, right? But in GFlowNets, usually we consider directed acyclic graph that multiple trajectory can list a single solution. So when we do the sequential generation, we can consider that diverse paths to generate a single sequence. So for example, we can generate sequence with left-handed and right-handed and together, right? So when you want to generate this GTCAGA, we can start it from TAG or whatever, and we can expand our sequence to the left or right or combination of this. So we consider this state space. And so, and there is very subtle point that how to measure this capability of generating model in this task. So we do not aim to find a maximum, right? So just a maximum liberty seeking, but we want to make some very good sampler. So theoretically, we have to measure some probabilistic gap between exact sampler and our generated sampler, but it is almost impossible because we have too many regions that we cannot, it is intractable to measure that probabilistic gap properly. So yes, in this study, we measure the average leeward from the sampler, and we measure diversity, we measure and number of modes. The number of modes means that the number of data points that above the threshold levered, and they have to be dissimilar themselves. So we we can suppose if we find a proper number of modes, we can capture very good probability distribution. Okay. And in sampling accuracy, this is expectation ratio of the exact sample. Okay. Question from Emmanuel. Right?
Yeah, sorry, there's another question in the chat from
Yeah.
Jason.
Chat. Okay. So Jason, how are the flow related to the modes? There are states and structured queries. So yes, thank you for the question. So modes means that terminal states, right? So we want to generate structures like a molecule, and this is defined with the terminal states. And this flow will finalize with the terminal states. And the amount of the flow in the terminal states had to be same with the leeward. And mode means that data point, the terminal states that has leeward above the threshold, and they have to be dissimilar so that our flow have to find terminal states that has high leeward and diverse terminals. So flow have to model properly for this. Yeah. So did I answer? Okay, good. So most simple way to measure is just compare the average. So expected value of the leeward. So indeed, this is not a perfect method to measure probability gap, but we can say if it is not accurate, they have a large probability gap. So if we get a 100% on this metric, this not say that is perfect generative model, but at least we have to get a very good sampling accuracy, at least, right? So in previous study of GFlowNets, that there's many objective function I introduced, like detailed balance or trajectory balance, and others. And when you see the performances, they are far below our expected leeward value. So 100% is our expected, but far below. When we use local search GFlowNets, we can improve these accuracies substantially over every task and every objective function. And when you see this graph, this will really improve also sample efficiency. So reduce training round, and we can accelerate the training faster. And yes, there is number of mode metrics, as you can see similarly. So in every objective function and every task, this local search tree can improve to seek the modes. So as you see in the graph, it substantially improved over baselines. And also, so this is another important point that, so we don't have exact metric to measure probability gap. So we will use number of modes metric that have two conditions. That first, the data point have to beyond the threshold leeward, but second, they have to be dissimilar. But how, so what is the threshold of the dissimilarity is that is also very sensitive hyperparameters for measure these performances. So we do for a lot of hyperparameter for that to measure this similarity. So for example, for QM9 test, we measure Tanimoto diversity for measure similarity, and so we did experiments on over many constraints. Oh, there's questions from John. What does it mean by LS-GFlowNet hierarchical exploration? Yeah, so hierarchical exploration means the first GFlowNets find diverse candidate and local search refine these candidates for better labor. So I say hierarchical because GFlowNet and local search, yeah, this hierarchy. Okay. And we can also consider that mode should be local optimal of some region. So we can measure the local region of data point, and they have to be local maximum. So we can consider the one Hamming from this one data point and see they are local optimal or two Hamming or three Hamming. And if there is infinite Hamming, they have to be global optimal. So increasing this constraint Hamming means the seek so increasing number of modes is more difficult. And so in this setting, yes, local search GFlowNets help to find these kind of challenging modes. So yeah, I think in many environmental setting, local search GFlowNets yeah, consistently improve over the baselights. And yes, we can compare with other reinforcement learning algorithm because we have similar structure of generating structure by because this can be seen the agent system of the sequential decision making. So maybe we can use a PPO or the actor-critic with some entropy bonus for the diversity. But even we use entropy bonus, even we tune hyperparameter massively, these performance from reinforcement learning is not enough, as you see in the graph. So usually GFlowNets methods are far better than the reinforcement learning for this kind of metrics. So when we want to seek diverse candidates in the molecule graph, GFlowNet is better than reinforcement learning, and local search trick will improve even over the GFlowNets. Right. So, and this is the last experiment that our algorithm can be seen as MCMC, and we can measure our acceptance rates of MCMC sampling. In every transition, we can measure acceptance rate. So I just measured acceptance rates over training iterations, and surprisingly, they have very stable constant line over training rounds of acceptance rates. So higher acceptance rates means that local search improved a lot from their reference. So when they propose another sample, the proposed sample is substantially better than the original sample. If acceptance rate is too low, this means the proposal corner is too poor, right? This not improve any reference point, right? But when these go like constant line, we can infer that first, the candidates generate from GFlowNets are improving over and over. And recall our local search is derived by also GFlowNets. We use the backward policy and forward policy using training GFlowNets. So quality of the local search will be also improved over the training round. So because they are improved together, these acceptance rates are constant. So we can say that this kind of improvement, like self-improving system, can make very good samples by mixing GFlowNet and MCMC. So this can be further work. So this is also submitted in this ICML that one can say that we can, so we know that local search tree can improve the GFlowNet capability. What if we don't use the back and forth local search, but other domain-specific local search? So in molecule generation or molecule optimization, genetic algorithm is classical algorithm, but it is really powerful in this domain. So what if we use genetic algorithm as local search method? So integrate GFlowNet and genetic algorithm. So I tried that. And after we got a really substantial performances in very popular benchmark called practical molecule optimization. So this benchmark benchmarked over 20 baselines, including reinforcement learning, genetic algorithm, Bayesian optimization, or others. And they measure sample efficiency so that they measure area under curve of 10,000 oracle calls of main metric, and there is many oracle function that includes some binding activity and how similar with target structure and some multi-objective based objective function and others. And based on these oracles, so this is very massive benchmarks, and using genetic guided GFlowNets, so that we use local search as genetic algorithm that gives a really good performance over other competitive baselines. So they can be really good further works that in molecule field we can use. There's many domain specific search method, not only for genetic algorithm. So we can integrate them into the GFlowNets, so one can use them for practice. Okay. Thank you for listening. So, and there's question from Oleg, what is genetic GFlowNet? So genetic GFlowNet is just local search GFlowNet that, so we use local search as genetic algorithm. Yeah. And question from Ho J. Sorry, question from Ryan. And so there's 3 questions. So, okay, in order, the order is most least interesting to me. Are you able to get unbiased estimate or underestimate of the test log likelihood after pre-training and again after fine-tuning? Also, are the samples you are generating complete unconditional with respect to level and properties? Am I right thinking accuracy is slightly equivalent to measuring the percent chance of a... Okay, there is many questions from Ryan. So in GFlowNets, there is no pre-training and fine-tuning, and we have online training process that run sampler over the training. So every training loop we will try to make exact samples, and we will collect some data points. And there is 2 ways to measure these kind of accuracies, that we can use the samples historically collected over training loops, and we can also use sample from current trained policy, and we can make a model that able and just make like test samples to measure the performances. So for number of modes, this is evaluated by historically collected data point over the training. And we measure other metric like leeward or the accuracy we measure in the test samples. And unbiased estimate. Now, I don't really understand what is unbiased estimate mean, but every GFlowNets loss, so at least trajectory balance is unbiased estimator, but have a high variances, and detailed balance is biased estimator. If not, they have 0 for every support space. They are biased because they use their flow models, and these flow model are inaccurate in general. So yeah, it will be biased, but it is very short. It focused the short trajectory, so less variances. But in general, the trajectory balance condition can make unbiased estimator for target distribution. And the last question is that accuracy slide. It's equivalent measuring percent. No. It's not about the metropolis-Hastings stochastic filtering acceptance accuracy, but is like how. So this accuracy is a ratio that. So we have exact sampler. So our target sampling distribution. So we know our target expected leeward, and we compare this target expected leeward and our expected leeward. So this is sampling accuracy, I said. And okay. Pre-training and fine-tuning. So, and Ryan clarified that pre-training and fine-tuning is from these genetic GFlowNets slides. And yes, there's no problem, because like we will do pre-training with maximum likelihood estimation over the reference sets, and we will do the KL constraint for this reference, and we will do the fine-tuning for like for GFlowNets objective, and this can be seen as our prior distribution is our, so this pre-trained with GINC data. So this data set can be prior distribution, and our posterior distribution is like prior times that maybe leeward divided by Z. So this can be posterior inference using GFlowNets. So yes, this can be very good. This. Okay. And question from Jose that do you show us example of trajectory of DNA and RNA? Could you give example of the trajectory for molecule? Yes, that's a good question. So for these experiments, I use molecule just with 2 stem points, so that this can be extended. There is predefined action space of the molecule. So for QM9, we can choose action with atom and with 2 stem point. And in SEH, we can also take action for taking some predefined fragment. And this is really similar, just do the sequence generation of left-hand side and right-hand side. Yes, but indeed we can increase the number of stem points, maybe triple, or there can be 4 stem points. Then that makes more complicated. But in this experience, we did a very simple small molecule with 2 stem points. That makes very similar MDP with the sequential generation. And question from Alex that are potential loops on issue here? Sorry, I don't get this question. All right. Can you clarify this question? Potential loop. Okay.
I
Because
think you
this
muted.
MCMC.
Sorry.
Sorry. Okay. Yeah, I was muted. It's unclear to me that there cannot be any cycles here when you're adding and removing pieces of trajectory. Maybe it's self-evident, obvious, but not so obvious, because you could go into potential loop, adding a piece and removing a piece and getting back into the same very point in your sampling. No, it's not possible. It would be possible. And if there is a loop, how do we deal with it?
That's very good question. So using this kind of MCMC, that will this MCMC assume that we have we can visit every state possible. So this is not DAG in MCMC, right? But so we can split this process. So when we use MCMC local search, we will use that terminal states. And so back to the GFlowNet training, we will use DAG structure. So that's not that problem. So we only have a finite number of iteration in the MCMC. So these MCMC, MDP and GFlowNet MDP can be clearly separated, and they just can be just integrated very like, so they don't have to share their MDP, right? Okay. Okay, there is John's question about prepend append, but thank you, Emmanuel, to answer it. And is there another question?
I guess I have a question.
Yeah.
So in the original just local search paper, you use the backward policy that you train, I guess, with the model. And then you show with the genetic search that you can actually do much better in terms of local search with another backward policy, essentially. Have you thought about training the backward policy separately with, you know, RL or some other kind of method?
Yes, that's very good idea. So these kind of local search, the original local search relies on the quality of the backward policy. And backward policy is really crucial to find intermediate states that potentially drive into good points, right? And in this study, just naively trained with trajectory balance or other balance laws, but indeed we can use reinforcement learning, for example, for separately trained PB, the backward policy, and this will definitely improve the performances. So, but this local search GFlowNet is very general idea. This can be used for every domain, but the reason that genetic GFlowNet is better than local search GFlowNet in this target domain is that we use the domain-specific local search. So for this specific domain, I suggest people that if there is very good domain-specific local search tools, why not we just use them? But if we do not have that kind of things, we can use the general method that back and forth, and maybe we can use train better backward policy to improve over that performance there.
Yeah, makes sense. Thanks.
And there is Alex question that what does on policy, off policy mean in this context? Yeah, so on policy means we samples experiences from training policy, and off policy means there is behavioral policy that can be different with the training policy, that we collect experiences, simulate experiences from behavioral policy, and we use the that experiences. And as you can see, this illustration. So first, policy samples some molecule structure, and we can use genetic algorithm to refine it. And defined solution, defined experiences is not only from the training policy, and this is refined from other external policy. So this is of policy training, and local search GFlowNet is completely of policy training, right? Because they use local search for guiding exploration.